Hi guys, welcome back to my YouTube channel. I hope you have been getting some time to look at the videos and have been very helpful to you to prepare for your exams and to understand some concepts, right? Today I'm going to touch on electric field. So in previous video I went into questions and theory of electrostatics, electrostatic force, right? Today I'm just going to cover the electric field part of it. So when we talk about electric field, we are talking about a region of space where an electric charge will experience a force, right? So when you have an electric charge, remember we said electric charges can attract each other or repel each other. So within a certain distance, a electric charge can be able to experience attraction or repulsion if it's in an electric field, right? So when we are looking at electric fields, we can be able to calculate the magnitude of the electric field. So the electric field can have a certain strength depending on how close or how far a electric charge is, right, in the field or from another sphere in the field. So when you have, for instance, what we call, before I look at the examples, let's look at electric field strength at a point. Then it's the force experienced per unit positive charge at that point. Right. Electric field is the force experienced per unit positive test charge at that point. So that's the electric field strength at a point, right? So you can be able to quantify the strength of the electric field using either one of these two equations. This one now is, for instance, if you have two spheres, if you have two spheres, and then the question says treat sphere A as a point charge and then calculate the electric field experienced by A, right? So now you can use the force that is experienced between these two, right, charges. So if this is a negative charge, this is a positive charge, then it means there's an attractive force between the two. So you can calculate the magnitude of the force if you have the distance between the two. Let's say you're given the distance. Then you can calculate the electrostatic force. So that force that you can calculate using F is equal to K Q1 Q2 over R squared is the force that we are referring to here, right? So it's the force, the net force experienced by that object. The electric field is measured now in newtons, so obviously force is in newtons, and the charge is in coulombs, which means electric field is measured in newtons per coulomb, right? So you can be able to calculate the electric field using this formula But also keep in mind that electric field, like electrostatic force, is a vector. So it has magnitude and direction. So that is important when you're doing your calculations, right? Another formula that you can use to calculate electric field is E is equal to KQ over R squared. So here E is electric field, K is Coulomb's constant, which we already learned about, 9 times 10 to the power of 9. And Q is the charge that is creating the electric field, right? Then R is the distance between the two charges. So now, if for instance I was calculating for this very same question, let's say they said a point P is a certain distance between A and B, right? Or certain distance from B. Let's say it was 0.17 meters from B. Then the question says, calculate the electric field experience at P. Then I can be able to use the charge on B, right, as well as the charge on A to calculate the net electric field experience at P. Now, when I'm doing the distance, I must consider first the distance between B and P, which is 0.17, distance between now P and A, which is 0.37. So I can do two separate calculations to find the electric field experience at P due to B and the electric field experience at P due to A. Remember, it has direction, so you have to consider whether it's going to be in the positive direction or in the negative direction, which we're going to do when we do calculations, right? So when we talk about a point charge, this is always a positive test charge, right? So you can think of it as a positive test charge. Think of a hydrogen ion, right? So when you take like hydrogen, which has one electron, if you remove that one electron, then you get like a hydrogen plus, H plus. Then you have what we call a positive test charge, right? So the whole point is that the positive test charge is not meant to be contributing much to the electric field. It must be negligible. Its contribution must be negligible in the electric field. So that's why we use a positive test charge. Because remember, once you have a negative test charge, then it means you have an electron cloud around the nucleus, and then it means it has some contribution. So when you have a positive test charge, it's like basically having just a nucleus, right? So your positive test charge is either going to be attracted or repelled to A and B. That way you can be able to calculate the electric field experienced, right? So this is the distance between the two in meters. And then this is the charge in coulombs. And then this is going to be Coulomb's constant, right? And this is still going to be newtons per coulomb, and it's going to be a vector. So when you're calculating, you can either be given a scenario that is just in the form of words, or you can be given a graph. So you can get two graphs that represent electric field. Okay, can actually get three. I don't have space for the third one, so I'm going to do it on the next page. So you can have electric field versus 1 over r squared. You'll get a straight line from the origin, and then the slope is going to represent q. Or you can have e r squared. That's going to be a non-linear graph. So remember that you got relationships from this equation. Electric field directly proportional to the charge, electric field inversely proportional to the distance between the two, right? So that's how we're getting these two graphs here. And then you can also get another graph, which is E Q. Then from this graph, the slope is going to give you 1 over r squared, right? So from the graphs, you can also be able to calculate all those other values, the slope, using the slope. And then now, when you have an electric field, there's another way that we can represent it. We can represent it in what we call electric field lines, right? These are lines that are used to represent the electric field. So that's certain region where an electric charge will experience a force, right? So these lines, there's some properties that you must obey when you are drawing an electric field. The lines must not touch. The lines must be perpendicular to the object, which is often just the sphere. And the lines must be closer, right? Closer together where the electric field is stronger, right? So closer where electric field is strong. That's just my own edition. But the most important thing there is the lines mustn't touch and the lines must be perpendicular to the object, right? And also the shape of the lines is also important, which we're going to delve into just now. So let's say you have a positively charged object. Then I said you can represent the electric field around the object using what we call electric field lines, right? So these lines, they must not touch. Now they have direction as well. When you look at a positively charged object, how do you determine the direction, whether it's going to be, the arrows are pointing out or in? If I am to place a positive test charge in this electric field, what is going to happen is it's going to get attracted to this positively charged sphere or repelled. So that's what determines the direction of the electric field, right? So these two, positive and positive, will repel, which means the positive test charge will move away from the object. So the direction is basically, or the arrows are indicating the direction of a test charge if it was placed in that electric field, right? If I was to have a negatively charged sphere, and again, I was to place a positive test charge, it will be attracted to the negatively charged sphere. So the arrows point in for negative and out for positive, right? I can also be asked to draw the electric field between two positively charged spheres, which means since these two are going to repel, the lines must never touch since they repel each other, right? And then the arrows are going to be pointing out. So these for like charges. Or I can be asked to draw the electric field pattern. Electric field pattern for unlike charges. Right? So these attract each other. And then the arrows always point from negative to positive, right? Or rather from positive to negative, sorry. From positive to negative. Like that, right? So if you had been asked for two negatively charged spheres, obviously the electric field pattern will be the same as this one, but now the difference is the arrows will be pointing inwards, right? I hope that was helpful to just give you an idea of what we're talking about when we are talking about an electric field and how it's represented. I'm gonna again do another video where I'm going to cover now the questions that are around electric field, and I show you how we apply the fact that it's a vector and all of that in our questions. I hope that was really helpful. Please also look at the videos for electrostatic force and help. I hope it's going to help you to prepare for your examinations and while you study. Thank you for tuning in. Please like, please subscribe, and please recommend to all your friends. And any questions, please direct them in the comments, or please post them in the comments. See you on the next video.